In the immense emptiness of space, journeying at unfathomable velocities through the void separating the stars, a remarkable entity is nearing our solar system. 7 miles in width and composed of immaculate ice that predates our own planet, 3I Atlas is on a course so statistically unlikely that it resists a natural cause. Its trajectory will guide it beyond Mars, loop behind the Sun, approach Earth, and traverse Jupiter's magnetosphere in a progression that appears akin to a reconnaissance operation. My long-held assumption has been that entities from other star systems would be merely inert rocks and ice, cosmic fragments cast out from faraway worlds. But suppose that notion was mistaken. What if certain interstellar bodies are not accidental drifters, but instead intentional emissaries? Mute observers from civilizations that mastered the art of concealing themselves in the cosmic gloom long ago. This evening on The Sleepy Explorer, I will investigate the indications that our most enigmatic visitor could signify humanity's initial encounter with an extraterrestrial intelligence. I will delve into the Black Forest theory, interpret statistical anomalies, and explore the reasons why 3I Atlas acts differently from any celestial body I have ever observed. The cosmos might not be as vacant as I once believed. Ready yourselves. I shall commence. The Black Forest theory posits that technologically advanced societies stay intentionally concealed, employing advanced probes camouflaged as common celestial detritus to observe developing worlds such as Earth. In contrast to the enigmatic Oumuamua or the standard comet Borisov, 3I Atlas displays a meticulously planned route through our solar system, which seems engineered for the greatest reconnaissance advantage while preserving flawless camouflage. As this perplexing visitor embarks on its extensive tour past our planets, I am confronted with a prospect that could revolutionize my comprehension of life throughout the universe. Am I observing my first engagement with an extraterrestrial intelligence, or is this merely the most extraordinary cosmic coincidence in the annals of human existence? To resolve this query, I must examine the discovery of 3I Atlas more closely. The narrative of 3I Atlas does not start with a striking moment of insight, but rather with the systematic diligence characteristic of contemporary astronomy. On the 1st of July 2025, at the Atlas Observatory in Rio Hurtado, Chile, automated instruments registered a dim speck of light traversing against the backdrop of stars. Its preliminary label was the prosaic A11Pi3Z, a provisional marker that offered no clue as to the cosmic relevance this object would later acquire. Atlas, the Asteroid Terrestrial Impact Last Alert System, stands as one of mankind's most advanced early detection networks for objects with hazardous potential. With funding from NASA and operated by the University of Hawaii, Atlas is comprised of 4 telescopes placed strategically across the planet, each with the ability to survey immense portions of the sky on every clear night. While the system's primary design is to find asteroids that could endanger Earth, its broad-field prowess makes it uniquely suited for identifying atypical objects, such as visitors from interstellar space. The Discovery Telescope in Chile, a 0.5-meter reflector outfitted with cutting-edge CCD cameras, originally identified A11Pi3Z as just another moving object that necessitated additional observation. In the contemporary age of automated celestial surveys, telescopes register thousands of moving objects nightly. The majority prove to be asteroids from the main belt, near-Earth objects, or familiar comets making return trips to the inner solar system. The feature that rendered this specific detection unique was not instantly obvious. The object was dim, at an approximate magnitude of 19, signifying it was much too faint to be seen with unaided vision or even with basic amateur telescopes. Its movement against the stellar canvas was quite slow, implying it remained at a considerable distance from the Sun. These features by themselves would not have triggered any alerts within the automated analysis systems. The procedure for verifying an interstellar path is intricate and demands meticulous observation. The crucial parameter is orbital eccentricity, a figure that defines the ellipticity of an orbit. Bodies gravitationally tied to our solar system possess eccentricities below 1, indicating they follow closed elliptical paths around the Sun. Bodies with eccentricities exceeding 1 travel on hyperbolic paths, arriving in our solar system from interstellar space and ultimately departing, never to come back. The first observations of A11Pi3Z hinted at an eccentricity above 1. Yet such figures necessitate verification over several nights of accurate astrometry. Atmospheric disturbances, equipment inaccuracies, and the object's dimness all add to the uncertainty of the measurements. Numerous objects first thought to be interstellar have subsequently been identified as peculiar, yet solar system-bound, comets or asteroids following highly stretched-out orbits. In the days following the initial finding, observatories across the globe commenced tracking the object. The European Space Agency's optical ground station in Tenerife validated the high eccentricity readings. The Catalina Sky Survey in Arizona contributed further positional information. By the 6th of July, a sufficient number of observations had been gathered to dispel any uncertainty. This was, in fact, the third confirmed interstellar body to enter our solar system. The official naming procedure started right away. The International Astronomical Union's Minor Planet Center, the worldwide repository for small body findings, gave it the formal designation C2025-N1, Atlas, with the C prefix signifying a comet-like body, and the N1 indicating it was the first such object found in the latter half of July 2025. The informal name 3I Atlas came soon after, with 3I standing for the third interstellar object. The astronomical community's response was swift and powerful. Unlike the unexpected finding of Oumuamua, which had taken researchers by surprise, the scientific establishment had been gearing up for more interstellar visitors. Observational procedures had been formulated, theoretical models had been constructed, and financial mechanisms were prepared for prompt follow-up studies. Dr. Robert Warwick, who had found Oumuamua 8 years prior, remarked that the identification of 3I Atlas was both recognizable and completely new. The systematic verification process was comparable, but the object itself held the promise of being much more available for thorough investigation. In contrast to Oumuamua, which had already started its departure when it was found, 3I Atlas was still on its approach to the Sun, providing months of observational windows. The technical hurdles in observing 3I Atlas were considerable, but not insurmountable. At the time it was discovered, the object was located at a distance of about 5.2 astronomical units from the Sun, which is similar to Jupiter's distance. This implied it was getting very little solar warmth, and any cometary behavior would be faint and hard to notice. The object's luminosity was predicted to rise significantly as it neared its perihelion on the 29th of October, at which point it would be closest to the Sun at 1.36 astronomical units. Professional observatories quickly started organizing observation initiatives. The Hubble Space Telescope assigned discretionary time from its director for pressing observations. The James Webb Space Telescope readied its infrared spectroscopy schedules. Ground-based observatories worldwide adjusted their timetables to monitor this uncommon visitor. Amateur astronomers were also instrumental in the initial observation efforts. Philip Romanoff, observing from a distance through iTelescope.net's 0.51-meter reflector in Chile, took some of the very first confirmation pictures just a single day after the initial finding. His image, which displayed a dim blur against a backdrop of stars, was one of mankind's first views of this enigmatic visitor from another star system. As July turned into August, the early fervor started to be replaced by more organized study. Initial observations indicated that 3I Atlas was more than just another interstellar visitor. It was an entity that was potentially without precedent in both its scale and its actions. The foundation was laid for one of the most rigorous astronomical observation efforts in history. The discovery of 3I Atlas served as a reminder to the scientific world that our solar system is not a secluded haven, but more of a crossroads on ancient migratory paths that link the stars. Every visitor from interstellar space presents a distinct glimpse into the phenomena that form planetary systems across the galaxy. And 3I Atlas held the promise of offering the most unobscured view yet into these cosmic workings. When the initial size calculations for 3I Atlas started to surface from the observational data, the astronomy community felt something akin to a shared sense of wonder. Early photometric readings pointed to a diameter of around 7 miles, or approximately 11 kilometers, which established it as the largest interstellar object ever observed by a significant margin. To contextualize this dimension, Oumuamua, my first interstellar guest, was about 400 meters long and maybe 40 meters wide, even when considering its stretched, cigar-like form. Oumuamua's volume was insignificant compared to the generally spherical mass of 3I Atlas. Borisov, my second interstellar guest, was smaller still, with a nucleus projected to be less than 1 kilometer across. 3I Atlas surpasses both of its forerunners, holding over 1,000 times the volume of Oumuamua and possibly 10,000 times the mass. This stark disparity in size has far-reaching consequences for my comprehension of interstellar bodies and the phenomena that give rise to them. Tinier objects such as Oumuamua and Borisov could be readily accounted for as debris thrown out during the formation of planets or through gravitational interplay within their native systems. Larger bodies like 3I Atlas demand more spectacular origins, such as the shattering of a dwarf planet, the gravitational expulsion of a small moon, or the catastrophic fragmentation of a huge comet. The scale of 3I Atlas also bears considerable weight for its ability to endure during its journey between stars. The space separating stars is not completely void, but is filled with a sparse medium of gas and dust, cosmic rays, and infrequent collisions with other objects. Over the millions or billions of years needed for interstellar transit, smaller bodies can be steadily worn down by these influences. A 7-mile-wide object, in contrast, has enough mass and structural soundness to last almost forever in the interstellar medium. Perhaps most crucially, the substantial size of 3I Atlas enables it to hold on to volatile substances, like water ice, for exceptionally long durations. Smaller bodies possess a high ratio of surface area to volume, which means they lose volatiles rather swiftly through sublimation and space erosion. A large body such as 3I Atlas, however, can preserve an untouched interior for billions of years, essentially acting as a time capsule that safeguards the conditions of its original stellar system. Ascertaining the exact shape of 3I Atlas necessitated meticulous photometric study, which involved tracking how the object's brightness altered as it spun. These observations pointed to a rotation period of about 12.4 hours, indicating the object completes one rotation roughly every half of an Earth day. The rather small change in brightness during this spin suggests that 3I Atlas is more or less spherical rather than highly stretched out like Oumuamua. This nearly spherical form is quite noteworthy and offers significant hints about the object's origins and past. Extremely elongated bodies like Oumuamua imply they were either formed under intense tidal pressures or were possibly artificially made. Spherical bodies, on the other hand, generally come into being through accretion, a process that lets gravitational forces mold generally round forms, the very same process that created the planets and moons in my own solar system. The albedo, or the measure of reflectivity, of 3I Atlas turned out to be quite low, at about 0.04, which means it bounces back only about 4% of the sunlight that strikes it. This is characteristic of comet nuclei, which are often said to be darker than charcoal because of their high concentration of organic materials and carbon-rich minerals. The low albedo was in stark contrast to Oumuamua's unusually high reflectivity, offering another clue that 3I Atlas might be a more typical specimen of interstellar matter. Estimating the mass of distant objects is known to be very challenging, as it requires either gravitational disturbances on other bodies, which 3I Atlas was too distant and solitary to offer, or assumptions about its density based on its composition. By using spectroscopic information that pointed to a composition of ice and rock akin to comets from my outer solar system, scientists projected the mass of 3I Atlas to be around 1.2 trillion kilograms, comparable to a small mountain on Earth. This immense mass, together with the object's relatively untouched condition, indicated that 3I Atlas could harbor materials that date back to the creation of its parent stellar system. Unlike smaller interstellar bodies that might be made of processed or changed material, 3I Atlas could hold primordial ices and minerals that condensed directly from the protoplanetary disk around a faraway star. The density calculations, based on mass and volume figures, pointed to a value of approximately 0.6 grams per cubic centimeter, which is considerably less than solid rock, but is in line with a blend of water ice, organic materials, and rocky minerals. This density profile was consistent with theoretical models for large comet nuclei that form in the far reaches of planetary systems, where temperatures stay low enough for water and other volatile substances to condense. As observational findings were compiled throughout July and August of 2025, a depiction of 3I Atlas emerged as an untouched relic from the formative era of another stellar system. Its considerable size, low density, and spherical form all pointed to its creation through slow accretion in the cold, distant regions of a faraway planetary system, followed by its expulsion into interstellar space due to gravitational encounters with massive planets. Nevertheless, these seemingly clear physical traits would shortly reveal themselves to be merely the start of the enigmas associated with 3I Atlas. As more advanced observations started to unveil specifics about the object's composition and path, inquiries would surface that questioned straightforward explanations and paved the way for much more unconventional possibilities. The sheer magnitude of 3I Atlas, which dwarfed all preceding interstellar discoveries, marked a significant advancement in my capacity to examine material from other star systems. For the first time, astronomers gained access to an interstellar body substantial enough for in-depth compositional study, sophisticated trajectory simulation, and perhaps even missions for direct sample collection. The scene was prepared for breakthroughs that would alter my comprehension of both planetary formation phenomena and the likelihood of intelligence elsewhere in the galaxy. The composition of 3I Atlas stands as one of the most crucial findings in the study of interstellar objects, offering unparalleled understanding of the chemistry and formative processes of a remote stellar system. As the object neared the Sun during the summer of 2025, progressively more powerful telescopes focused on interpreting the spectroscopic clues concealed within its dim, reflected light. The initial major discovery originated from observations conducted with the NASA Infrared Telescope facility on Mauna Kea, Hawaii. Employing its high-resolution spectrometer, astronomers identified distinct absorption patterns consistent with water ice across various infrared wavelengths. This finding was not entirely unforeseen. Water ice is prevalent in comets throughout my own solar system. However, the properties of this ice revealed an extraordinary narrative. A thorough isotopic examination showed that the water ice in 3I Atlas is markedly different from water found anywhere in my solar system. The deuterium to hydrogen ratio, a vital indicator used to determine the origins of water, displayed values unlike anything seen in Earth's oceans, comets from the Kuiper Belt, or even the most ancient meteorites. This isotopic signature offered definitive proof that the water in 3I Atlas formed in a completely separate stellar context, perhaps 7 billion years ago. The untouched state of this ancient water ice is of immense scientific significance. The majority of water in my solar system has undergone numerous cycles of heating and cooling over 4.6 billion years. Comets that have approached the Sun have lost their surface layers through sublimation, while water in asteroids and planets has been changed by thermal and chemical actions. The water in 3I Atlas, however, seems to have stayed frozen and unchanged since its initial formation, preserving a direct account of the conditions in its system of origin. Further spectroscopic studies from the Gemini South Telescope in Chile uncovered the existence of organic molecules within the object's composition. Complex hydrocarbons, such as methane, ethane, and more advanced organic compounds, were found alongside the water ice. These molecules indicated that 3I Atlas originated in a region abundant in carbon and other heavy elements, possibly around a star with a different metallicity than my own Sun. The presence of carbon-rich minerals introduced another level of complexity to the compositional analysis. Spectroscopic traits consistent with organic polymers and kerogen-like substances suggested that 3I Atlas held substantial quantities of processed organic material. On Earth, such substances are usually linked to biological activities, but in space they can be created through purely chemical processes involving simpler organic precursors and radiation. Perhaps most fascinatingly, the organic compounds in 3I Atlas displayed isotopic ratios that pointed to their formation in an environment rich in oxygen. This finding suggested that the object came from a stellar system where oxygen was more plentiful relative to carbon than in my own solar vicinity. Such circumstances can occur around older stars that have experienced multiple cycles of nucleosynthesis, enriching their surrounding protoplanetary disks with heavy elements. A comparison with typical comets from my solar system highlighted stark contrasts that went beyond simple isotopic ratios. Comets that formed near my Sun generally show signs of thermal processing, even those that have spent most of their existence in the frigid outer reaches of the Kuiper Belt or Oort cloud. They contain minerals that could only form at high temperatures, which suggests they incorporated material that once existed close to the proto-sun before being moved outward. 3I Atlas, however, displayed no signs of such thermal processing. Its mineral makeup seemed consistent with condensation at exceptionally low temperatures, possibly under 30 Kelvin. This implied it formed in the most distant regions of a faraway stellar system, far from the warmth of its parent star. The absence of high-temperature minerals indicated that 3I Atlas formed in place in the cold outer disk of its birth system, rather than assimilating materials transported from inner zones. The scientific significance of this untouched composition goes far beyond a mere curiosity about distant worlds. 3I Atlas is a direct sample of protoplanetary disk material from another star, enabling astronomers to verify theoretical models of planet formation under varied chemical and physical circumstances. The object functions as a natural laboratory for investigating how stellar metallicity, disk temperature, and other variables affect the kinds of materials available for building planets. The identification of complex organic molecules also has major implications for astrobiology. Although these compounds could have been formed through non-biological means, their existence in an untouched interstellar object shows that the chemical building blocks of life can be created and endure over cosmic durations. This discovery lends support to the idea that organic chemistry is a natural result of stellar and planetary formation processes throughout the galaxy. As observations persisted through August of 2025, more compositional specifics came to light that would be vital for comprehending the object's path and actions. Trace elements found in the ice suggested it formed around a star with about 1.3 times the metallicity of my Sun, a star perhaps 2 billion years older than my own. This greater age could account for the unusual isotopic signatures and the abundance of processed organic materials. The nitrogen isotope ratios in 3I Atlas also offered hints about its origin. The 14N to 15N ratio pointed to formation in a stellar environment with different nucleosynthetic processes than those that created the materials in my solar system. This isotopic signature might eventually allow astronomers to pinpoint the specific type of star system from which 3I Atlas came. Perhaps most strikingly, the compositional study found no indication of significant space weathering or changes during the object's interstellar voyage. Despite potentially billions of years of exposure to cosmic radiation, galactic magnetic fields, and the interstellar medium, 3I Atlas seemed to have maintained its original composition with very little alteration. This preservation hinted at either a relatively brief interstellar trip or highly effective shielding of its internal materials by its outer layers. The pristine state of such ancient materials in 3I Atlas presents an unparalleled scientific prospect. For the first time, researchers can examine materials that formed around another star, kept in their original condition for billions of years. This cosmic time capsule provides insights into planetary formation, stellar chemistry, and the spread of life's essential components across the galaxy. However, as detailed compositional data was gathered, some researchers started to observe subtle irregularities that did not align perfectly with standard models of comet formation and evolution. These inconsistencies would soon fuel increasing speculation about whether 3I Atlas might be something more intricate than a simple interstellar piece of ice and rock. The orbital course of 3I Atlas through my solar system marks one of the most statistically extraordinary paths ever documented for a celestial body. As astronomers honed their calculations throughout the summer of 2025, the mathematical exactness of the object's journey began to provoke questions that tested conventional theories of natural orbital dynamics. 3I Atlas is approaching my solar system on a sharply inclined retrograde orbit, which means its motion is opposite to that of the planets orbiting the Sun. This retrograde path is not in itself uncommon for interstellar bodies, as visitors from other star systems can arrive from any direction in three-dimensional space. What makes this trajectory exceptional is its precise alignment with the fundamental planes of my solar system. The object's orbital plane has an inclination of 162 degrees relative to Earth's orbital plane, positioning it in what astronomers refer to as a nearly polar retrograde orbit. While this may seem arbitrary, a thorough analysis shows that this inclination results in an alignment that optimizes the object's visibility from Earth for its entire journey through the inner solar system. By what appears to be sheer chance, 3I Atlas will stay observable from Earth-based telescopes for the duration of its visit, never vanishing behind the Sun for long intervals as most objects do. The trajectory features a sequence of planetary encounters that seem almost orchestrated to provide maximum opportunities for scientific observation. On the 3rd of October, 2025, 3I Atlas will pass within 18 million miles of Mars, a proximity that allows for detailed study by several spacecraft currently in orbit around the red planet. The timing of this encounter places it during the Martian dawn, when observation conditions will be ideal for spotting any development of a coma or tail as the object nears its closest point to the Sun. After its encounter with Mars, 3I Atlas will reach perihelion on the 29th of October, 2025, at a distance of 1.36 astronomical units from the Sun. This perihelion distance positions the object just beyond Earth's orbit, far enough to prevent significant gravitational disruption, but close enough for maximum solar heating and potential coma formation. The timing of perihelion on the opposite side of the Sun from Earth presents a natural observational hurdle that can only be surmounted by spacecraft located at the L1 Lagrange point or in orbit around Mars. The post-perihelion path continues the sequence of seemingly optimized planetary meetings. On the 19th of December, 2025, 3I Atlas will pass at a distance of approximately 170 million miles from Earth. This is close enough for thorough observation with the James Webb Space Telescope and the Vera C. Rubin Observatory, yet far enough to preclude any gravitational effect on either the object or my planet. The most extraordinary encounter is set for the 16th of March, 2026, when 3I Atlas will travel just 33 million miles above Jupiter's cloud tops. This proximity places the object deep within Jupiter's magnetosphere and near enough for potential sample collection by the Juno spacecraft. The geometry of the encounter indicates that 3I Atlas will traverse regions of Jupiter's magnetotail where charged particles and dust from the object could be captured and examined. A statistical review of this trajectory shows probabilities so minuscule that they challenge standard assumptions about random orbital mechanics. The exact alignment with Earth's orbital plane has less than a 0.2% chance of happening randomly. When considered with the specific distances and timing of the planetary encounters, the overall likelihood falls to about 1 in 20,000, a figure statistically significant enough to justify serious thought about non-random causes. The trajectory also displays features that would be perfect for a reconnaissance mission aimed at studying the major planets of my solar system. The sequence of encounters permits detailed observation of Mars, an optimal approach to the Sun for instrument calibration and power collection, strategic placement relative to Earth for communication or observation, and a close pass by Jupiter for sampling the largest planetary magnetosphere in the solar system. If 3I Atlas were an artificial probe created to investigate my solar system, its path would be hard to surpass. The route offers access to various planetary environments, maintains ideal positioning for solar power generation, and incorporates natural periods of concealment when the object is obscured by the Sun or at its greatest distance from Earth-based observers. Additionally, the high incoming speed of 3I Atlas at about 33 kilometers per second relative to the Sun points to an origin outside the local galactic vicinity. Objects cast out from nearby star systems typically arrive at lower speeds due to the gravitational pull of the Milky Way's stellar population. The high velocity of 3I Atlas suggests either an origin from a very distant stellar system or an artificial boost beyond what natural gravitational slingshot maneuvers could achieve. The retrograde nature of the orbit also facilitates efficient collection of solar system material that would be hard to obtain with a prograde path. As 3I Atlas moves against the general current of solar system material, it encounters a greater flow of dust, charged particles, and other debris that could offer information about the chemical and physical characteristics of my star system. Gravitational modeling of the trajectory uncovers another fascinating feature. The path seems to be meticulously optimized to bypass close encounters with the outer planets during its approach. Saturn, Uranus, and Neptune are all positioned so that their gravitational effects on 3I Atlas are kept to a minimum, preventing any major trajectory changes that might disrupt the carefully arranged sequence of encounters in the inner system. Some researchers have observed that the trajectory has striking resemblances to routes calculated for hypothetical interstellar probe missions that human space agencies have proposed. Studies by NASA, ESA, and other organizations have determined optimal paths for missions to nearby star systems, and many of these theoretical routes share features with the actual path of 3I Atlas through my solar system. The precision of the trajectory becomes even more notable when considered in light of the challenges of interstellar navigation. Any object journeying between star systems must factor in stellar movement, galactic rotation, and gravitational pulls from multiple sources. To attain the level of accuracy displayed by 3I Atlas would necessitate either exceptional luck or advanced trajectory planning and adjustment capabilities. Those who criticize the artificial origin hypothesis argue that confirmation bias may be shaping the interpretation of what could simply be a remarkable coincidence. With billions of objects in the galaxy and countless possible paths, even highly improbable events are bound to happen occasionally. The human inclination to perceive patterns and intent in random occurrences might be assigning artificial meaning where none is present. However, the mathematical fact of the trajectory's precision is hard to ignore. Whether it is the result of a cosmic fluke or intelligent planning, the path of 3I Atlas through my solar system is one of the most finely tuned displays of celestial mechanics ever witnessed. As the object proceeds on its journey towards perihelion, the true nature of its exceptional trajectory may at last be unveiled through direct observation of its behavior under solar warmth and gravitational pull. The voyage of 3I Atlas through my solar system proceeds with a precise celestial timing that provides unparalleled chances for scientific study. Each significant point in this path is a distinct opportunity to understand the object's real nature, with timing and placement that seem almost engineered to enhance my grasp of this enigmatic visitor. The 3rd of October, 2025, Mars Flyby. The first key event happens when 3I Atlas passes within 18 million miles of Mars, coming closer to the red planet than any previously seen interstellar object. This meeting occurs during the Martian dawn, offering ideal lighting for both orbital and surface-based observations. Several spacecraft now operating in orbit around Mars will have unmatched access to the object during this flyby. NASA's MAVEN, the Mars Atmosphere and Volatile Evolution mission, designed to examine the Martian upper atmosphere, will have the capability to spot any gas emissions from 3I Atlas with its array of spectrometers. The European Space Agency's Mars Express orbiter will provide high-resolution imaging, while China's Tianwen-1 orbiter will offer additional observational viewpoints. Ground-based observers on Mars, such as NASA's Perseverance and Curiosity rovers, might be able to capture images of the object if the atmospheric conditions allow. The timing of the flyby during the dawn hours means the object will be set against a dark sky, improving the contrast for photographic observations. This Mars encounter is especially important because it happens while 3I Atlas is still nearing the Sun and before significant cometary activity is anticipated to start. Any coma or tail seen during this time would suggest either a peculiar composition or artificial outgassing, as natural comets usually do not show a visible coma until they are within 2 to 3 astronomical units of the Sun. The expected angular size of 3I Atlas during the Mars flyby will permit extraordinary detail in imaging studies. If the object holds its projected 7-mile diameter, it should be visible as a resolved disk in high-resolution images, possibly showing surface details, rotation patterns, and any lopsided outgassing. The 29th of October, 2025. Perihelion. The most dramatic moment in the journey of 3I Atlas will be when it reaches perihelion at 1.36 astronomical units from the Sun. At this closest point, the object will undergo maximum solar heating, with temperatures high enough to sublimate water, ice, and other volatiles from its surface. The object's speed will reach a peak of about 152,000 miles per hour relative to the Sun. Regrettably for observers on Earth, perihelion happens when 3I Atlas is positioned on the far side of the Sun from my planet, obscured by solar glare and unobservable with ground-based telescopes. This timing presents both difficulties and chances for the scientific community. The main observational tools during perihelion will be spacecraft located at the L1 Lagrange point, about 1 million miles sunward of Earth. The Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory will be able to track 3I Atlas as it goes around the Sun, using coronagraphs designed to obscure the Sun's bright disk while showing dimmer objects in the surrounding corona. Observers based at Mars will keep their favorable position during perihelion, as the red planet's orbital location puts it roughly at a right angle to the Earth-Sun 3I Atlas line. This arrangement means that spacecraft at Mars can watch 3I Atlas during its time of greatest solar heating without being affected by solar glare. The perihelion passage is the ultimate test for the conflicting theories about the nature of 3I Atlas. If the object is a natural comet, the greatest coma development and tail formation should happen at this time. The lack of expected cometary activity or the appearance of unusual emission patterns could lend weight to more unconventional explanations for the object's origin. The solar heating during perihelion will also put any artificial components under extreme thermal pressure. Materials not made for the space environment could fail catastrophically, while advanced alien technology might reveal itself through unexpected thermal signals or controlled outgassing. The 19th of December, 2025, Earth distance check. As 3. Atlas continues its journey away from the Sun after perihelion. It reaches a key milestone on the 19th of December when it passes about 170 million miles from Earth. This distance puts the object just past Mars's orbital path, making it reachable by Earth's most powerful telescopes while guaranteeing no gravitational interference with my planet. The 19th of December observation period is vital because it is the first chance for in-depth Earth-based study of 3I Atlas after its perihelion passage. Any alterations in the object's look, composition, or behavior due to solar heating will be plainly visible during this time. The James Webb Space Telescope will be central to these observations, using its unparalleled infrared sensitivity to examine the chemical makeup of any coma or tail that forms. JWST's spectroscopic abilities can identify trace gases at concentrations far lower than what ground-based instruments can detect, potentially uncovering exotic materials or unusual isotopic ratios that might suggest an artificial origin. The Vera C. Rubin Observatory, with its huge 8.4-meter primary mirror and advanced digital camera, will carry out intensive photometric surveillance to spot any slight changes in the object's brightness or color that could signal ongoing activity or structural changes. The December observations are also important because they happen when 3I Atlas will be crossing the plane of the solar system, which maximizes its interaction with solar wind particles and interplanetary dust. Any artificial systems designed to gather samples of solar system material would be most active during this part of the trajectory. Ground-based radio telescopes will also concentrate on 3I Atlas during this time, looking for any electromagnetic signals that might point to active electronic systems. The object's distance will be perfect for radio observations, close enough for strong signal detection, but far enough to steer clear of interference from solar radio emissions. The 16th of March, 2026, Jupiter Pass. The most scientifically rewarding encounter in the journey of 3I Atlas takes place on the 16th of March, 2026, when the object passes just 33 million miles above Jupiter's cloud tops. This close approach puts 3I Atlas well inside Jupiter's strong magnetosphere, creating special opportunities for both passive observation and active sampling. NASA's Juno spacecraft, currently orbiting Jupiter, will be in a position to make detailed observations of 3I Atlas during the encounter. Juno's set of instruments, designed to study Jupiter's internal structure and magnetic field, will be uniquely suited to detect any interactions between the interstellar object and Jupiter's magnetosphere. The passage through Jupiter's magnetosphere will expose 3I Atlas to intense radiation and a barrage of charged particles. Any artificial systems would require sophisticated shielding to withstand this environment, while natural materials might show characteristic reactions to the radiation exposure that could be detected by Juno's instruments. Of special interest is the chance that Juno might be able to collect dust particles shed by 3I Atlas during the encounter. Jupiter's powerful magnetic field can trap charged dust particles, and Juno's dust detector might capture direct samples of interstellar material for the first time in human history. The gravitational interaction between 3I Atlas and Jupiter will also provide the final, conclusive measurement of the object's mass. By accurately tracking how Jupiter's gravity affects the object's path, astronomers can calculate its mass with unmatched precision, resolving any lingering doubts about its density and internal structure. The Jupiter encounter is the last major event in the journey of 3I Atlas through my solar system. After this flyby, the object will start its final departure into interstellar space, slowly fading from sight as it travels beyond the range of even my most powerful telescopes. post-Jupiter trajectory, and final observations. Following the Jupiter encounter, 3I Atlas will proceed on its hyperbolic path, eventually exiting my solar system for good. The object's post-encounter trajectory will be slightly altered by Jupiter's gravity, offering more information about its mass and structure based on the precise degree of this gravitational deflection. Final observations of 3I Atlas will likely go on through late 2026 and perhaps into 2027, depending on the object's brightness and the capabilities of future telescopes. These final glimpses will be especially useful for spotting any long-term changes in the object's behavior or appearance that might not have been noticeable during its short trip through the inner solar system. The complete timeline of the journey of 3I Atlas is an unprecedented chance to study an interstellar object under a broad range of conditions, from its cold, inactive state during its approach through the maximum solar heating at perihelion to its passage through Jupiter's harsh radiation environment. Every stage of the trajectory offers unique insights into the object's true nature. Whether 3I Atlas turns out to be a natural relic from another star system or something more extraordinary, its precisely timed journey through my solar system will give scientists observational data that will be studied and debated for decades to come. The trajectory itself has become as much a focus of study as the object's physical properties, posing fundamental questions about the role of chance versus design in cosmic mechanics. The dark forest theory, made famous by Chinese science fiction writer Liu Cixin in his acclaimed three-body problem trilogy, offers one of the most unsettling potential answers for the apparent quiet of the universe. Also referred to as the dark forest hypothesis, this idea tackles the renowned Fermi paradox, the perplexing conflict between the high likelihood of extraterrestrial civilizations and the total absence of any proof of their existence. The theory gets its name from a chilling analogy presented in Liu Cixin's writing. The universe is compared to a dark forest where every civilization is a hunter, moving silently among the trees. The instant any hunter gives away their position by making a sound, they risk being found and taken out by other hunters who see them as possible dangers. In this cosmic forest, silence is survival, while being discovered means death. The core reasoning of the dark forest theory is based on several key premises about the nature of civilizations and how they interact. First, it presumes that survival is the main objective of any civilization. Second, it states that civilizations cannot be sure about the intentions of other civilizations they meet. Third, it proposes that technological progress will inevitably result in the ability for interstellar destruction. Lastly, it contends that the distances and communication lags inherent in interstellar space make peaceful first contact nearly impossible. Based on these assumptions, any civilization that finds another is faced with an impossible decision. They cannot know if the found civilization is peaceful or hostile. They cannot communicate effectively because of the huge distances and time delays involved in interstellar messages. They cannot assume that even a currently peaceful civilization will stay peaceful as it continues to advance technologically. The logical course of action, therefore, is an immediate preemptive attack, which the theory calls a dark forest strike. This sets up a cosmic Mexican standoff where every civilization stays quiet and hidden, knowing that being found by another civilization probably means destruction. Advanced civilizations create increasingly sophisticated camouflage and stealth technologies while constantly watching for signs of others. The galaxy becomes filled with hidden observers, each one afraid to show themselves but frantically trying to find others before being found themselves. The implications of the dark forest theory go far beyond a simple game of hide-and-seek between civilizations. It suggests that advanced civilizations would create vast passive surveillance networks using complex probes and monitoring stations to collect information about potential threats while keeping their own presence hidden. These reconnaissance systems would need to seem completely natural to avoid being detected, posing as asteroids, comets, or other harmless space junk. In the context of 3I Atlas, the dark forest theory offers a way to interpret the object's strange characteristics and trajectory. If the theory is correct, then what I see as an interstellar comet might actually be a sophisticated surveillance probe designed to study my solar system while maintaining a perfect disguise as a natural object. The size of 3I Atlas becomes especially important in this view. A 7-mile-wide object provides plenty of room to hide advanced instruments, power sources, and data processing systems while keeping the outward appearance of a natural comet. The object's large mass would offer excellent protection against cosmic radiation and solar heat, safeguarding sensitive electronics during the long journey between star systems. The path of 3I Atlas also fits remarkably well with what a dark forest reconnaissance mission might try to achieve. The carefully planned sequence of planetary flybys maximizes observation opportunities while reducing the risk of being discovered through unusual behavior. The timing of perihelion on the far side of the Sun from Earth creates a natural period of hiding during which any artificial systems could work without the risk of being seen by my most sensitive instruments. The pristine composition found in 3I Atlas could be either genuine ancient materials saved from another star system or a sophisticated fake designed to trick spectroscopic analysis. Advanced alien technology could easily be able to create artificial ice and organic compounds with isotopic signatures that perfectly copy materials from distant stellar systems. Under the dark forest scenario, the goal of 3I Atlas would be to gather comprehensive intelligence about my solar system and its potential inhabitants. The probe would be designed to evaluate my technological abilities, watch my communications, analyze my planetary environments, and decide whether humanity is a current or future threat to its creators. The probe might have advanced passive sensors capable of detecting electromagnetic signals from Earth, analyzing my atmospheric composition for signs of industrial activity, and monitoring my space-based assets for evidence of advanced technology. It might even have active scanning systems that only work during times when they are shielded from Earth-based observation, such as during the perihelion passage behind the Sun. The dark forest theory also explains why such a probe would eventually leave my solar system instead of staying for long-term observation. A longer presence would increase the risk of being found and could potentially reveal the probe's artificial nature through subtle behavioral quirks. A single flyby mission, however, could gather extensive intelligence while keeping up a perfect disguise as a natural interstellar object. Critics of applying the dark forest theory to real astronomical observations point out several major issues with this interpretation. The theory assumes that all civilizations develop along similar technological and social paths, which may not reflect the true variety of possible evolutionary outcomes. It also assumes that interstellar destruction is both possible and better than other forms of interaction, which is speculative given my limited understanding of advanced technology. Furthermore, the theory depends heavily on game theory assumptions that may not apply to alien psychology or decision-making. Human ideas of threat assessment, risk management, and strategic thinking might be completely irrelevant to genuinely alien intelligences that evolved under different environmental and evolutionary pressures. The dark forest theory also has trouble explaining why a civilization advanced enough to build interstellar reconnaissance probes would be worried about a species as technologically primitive as current humanity. Any civilization capable of interstellar travel would presumably have technological advantages so great that early-stage civilizations like mine would pose no real threat for thousands or millions of years. Despite these criticisms, the dark forest theory is still compelling because it provides a consistent explanation for both the Fermi paradox and the unusual characteristics of objects like 3I Atlas. It suggests that the universe might be full of intelligent life, but that this life stays hidden behind layers of technological sophistication that make it almost impossible for less advanced civilizations to detect. Whether or not the dark forest theory accurately describes the true state of galactic civilization, it serves as a useful framework for evaluating unusual observations, like 3I Atlas. By considering the possibility that interstellar objects might not always be what they seem, I open myself to finding signs of intelligence that might otherwise be written off as natural phenomena. The theory also highlights the potential dangers associated with my own growing technological abilities and increasingly noticeable presence in the galaxy. If the dark forest theory is correct, humanity's radio signals, space exploration activities, and other signs of technological development might have already drawn unwanted attention from hidden observers throughout my local galactic neighborhood. Dr. Abraham Avi Loeb, the Frank B. Baird Jr., professor of science at Harvard University and former head of Harvard's astronomy department, has become one of the most well-known and controversial figures in the search for evidence of extraterrestrial intelligence. His readiness to seriously entertain artificial origins for unusual astronomical events has set off a heated debate within the scientific community, especially in his analysis of interstellar objects like Oumuamua and now 3I Atlas. Loeb's venture into the world of controversial ideas started with Oumuamua, the first confirmed interstellar visitor to my solar system. When that cigar-shaped object showed unexplained acceleration away from the Sun without any signs of cometary outgassing, most astronomers suggested various natural explanations involving strange forms of sublimation or structural oddities. Loeb, however, took a different route, proposing that Oumuamua's behavior was consistent with artificial construction, specifically a light sail pushed by solar radiation pressure. This hypothesis, explained in his book Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, established Loeb as either a visionary willing to challenge traditional thinking or a respected scientist who had gone too far into speculative territory, depending on one's viewpoint. Regardless of the final truth of his Oumuamua hypothesis, Loeb's approach showed the importance of considering all possibilities when faced with truly unusual observations. With the discovery of 3I Atlas, Loeb has once again come forward with hypotheses that challenge conventional interpretations. In a paper co-written with Dr. Carson Eyal of the Harvard-Smithsonian Center for Astrophysics, Loeb contends that 3I Atlas shows characteristics that are not only consistent with artificial construction, but may actually be more easily explained by technological rather than natural origins. The main point of Loeb's 3I Atlas hypothesis is based on the object's unprecedented size among interstellar visitors. At 7 miles in diameter, 3I Atlas is big enough to hide almost any kind of advanced instrumentation while keeping a believable outward appearance as a natural comet. Loeb argues that this size is in a Goldilocks zone for interstellar reconnaissance, large enough for sophisticated technology, but not so large as to be obviously artificial. According to Loeb's analysis, the size of 3I Atlas offers several benefits that would be highly desirable for an artificial interstellar probe. First, the large mass provides excellent radiation shielding, protecting sensitive electronics during the potentially million-year journey between star systems. Second, the substantial volume allows for redundant systems and long-term power sources that could operate for geological timescales. Third, the size enables the probe to carry comprehensive analytical equipment for a detailed study of target systems. Loeb also points to the object's high inbound velocity as evidence of possible artificial acceleration. At 33 kilometers per second relative to the Sun, 3I Atlas is approaching faster than most natural interstellar objects, which typically arrive with velocities between 20 and 30 kilometers per second. While this difference might seem small, Loeb argues that it could indicate artificial acceleration beyond what natural gravitational slingshot effects could produce. The retrograde trajectory of 3I Atlas also plays a prominent role in Loeb's hypothesis. While retrograde orbits are not unusual for interstellar objects, Loeb notes that this particular trajectory provides optimal conditions for a comprehensive solar system reconnaissance. The retrograde motion maximizes the object's interaction with solar system material, while the specific orbital inclination ensures optimal visibility from multiple planetary systems throughout the journey. Perhaps most significantly, Loeb emphasizes the statistical improbability of the precise sequence of planetary encounters of 3I Atlas. The trajectory that brings the object within observation range of Mars, through optimal solar heating at perihelion, past Earth at an ideal viewing distance, and finally through Jupiter's magnetosphere, represents a level of precision that Loeb argues is inconsistent with random gravitational mechanics. Drawing parallels to human space exploration, Loeb notes that the trajectory of 3I Atlas bears striking similarities to paths designed for my own interstellar probe missions. Projects like Voyager and Pioneer demonstrated humanity's willingness to send reconnaissance probes beyond the solar system, and theoretical studies by NASA and other agencies have calculated optimal trajectories for hypothetical missions to nearby star systems. Many of these theoretical paths share characteristics with the actual route of 3I Atlas. Loeb's hypothesis suggests that 3I Atlas might represent a sophisticated example of what he calls archaeological astronomy, the detection of technological artifacts from other civilizations through astronomical observations. Just as terrestrial archaeology reveals past civilizations through their material remains, Loeb argues that advanced civilizations throughout the galaxy might leave technological signatures that could be detected through careful analysis of unusual astronomical phenomena. The camouflage aspect of Loeb's hypothesis addresses one of the most common criticisms of artificial origin theories. Why would an advanced civilization go to such lengths to disguise their technology? Loeb suggests several possible explanations, ranging from scientific ethics, avoiding contamination of primitive civilizations, to strategic considerations, reconnaissance without revealing the observer's capabilities or origins. Loeb also addresses the composition analysis of 3I Atlas, suggesting that the detected water ice and organic compounds might represent either genuine ancient materials incorporated into the probe's construction or sophisticated biomimicry designed to fool spectroscopic analysis. He notes that an advanced civilization capable of interstellar travel would likely possess the technological sophistication to create artificial materials with any desired chemical and isotopic signatures. The timing of the arrival of 3I Atlas in my solar system also features in Loeb's analysis. He points out that the object's discovery comes during a period of rapid technological advancement for humanity, including the deployment of increasingly sophisticated space telescopes and the beginning of serious efforts toward interstellar communication and travel. This timing might not be a coincidence if 3I Atlas represents a reconnaissance mission designed to assess my technological development. Loeb's hypothesis extends beyond simple observation to suggest that 3I Atlas might be actively collecting samples of solar system material for analysis. The object's trajectory takes it through regions rich in interplanetary dust, solar wind particles, and other materials that could provide comprehensive information about my star system's composition and evolution. Such data gathering would be invaluable for any civilization considering future interactions with my solar system. Critics of Loeb's hypothesis argue that he consistently favors exotic explanations over more mundane alternatives, a tendency that some colleagues suggest undermines his scientific credibility. They point out that extraordinary claims require extraordinary evidence, and that the anomalous characteristics of 3I Atlas, while unusual, fall within the range of natural phenomena observed elsewhere in the universe. However, Loeb counters that the scientific method requires considering all possible explanations for observed phenomena, including those that might seem uncomfortable or unlikely. He argues that dismissing artificial origins a priori represents a form of anthropocentric bias that could prevent me from recognizing genuine signs of extraterrestrial intelligence. Loeb's approach to 3I Atlas reflects his broader philosophy about the search for extraterrestrial intelligence. Rather than waiting for obvious signals like radio transmissions, he advocates for actively looking for technological signatures in astronomical data that might reveal the presence of advanced civilizations. This approach, which he terms space archaeology, could potentially detect evidence of intelligence that doesn't rely on active communication attempts. The implications of Loeb's hypothesis, if correct, would be profound for humanity's understanding of my place in the universe. Confirmation that 3I Atlas represents artificial technology would provide the first definitive proof that I am not alone in the cosmos. It would also raise immediate questions about the intentions and capabilities of its creators and about what other artificial objects might currently be present in my solar system without my knowledge. Whether or not Loeb's specific interpretation of 3I Atlas proves correct, his willingness to seriously consider artificial origins for anomalous astronomical phenomena serves an important function in the scientific community. By pushing the boundaries of conventional interpretation, he forces other researchers to more rigorously defend their assumptions and consider alternative explanations they might otherwise dismiss. One of the most perplexing aspects of 3I Atlas involves what it hasn't shown rather than what it has. As the object continues its approach toward the Sun, astronomers have been conducting intensive searches for the characteristic chemical signatures that should accompany a natural comet of this size as it begins to experience solar heating. The absence of these expected signatures has become a central mystery that challenges the conventional understanding of cometary behavior. Traditional comets, formed in the cold outer regions of my solar system, contain a mixture of water ice, frozen carbon dioxide, methane, ammonia, and various organic compounds. As these objects approach the Sun, solar radiation begins sublimating these volatile materials, creating the characteristic coma and tail that make comets visible to amateur observers. This process begins gradually at distances of 5 to 6 astronomical units from the Sun and intensifies dramatically as the comet approaches perihelion. The specific gases released during this sublimation process create distinctive spectroscopic signatures that serve as fingerprints for cometary composition. Among the most readily detectable are cyanogen, Cn, and diatomic carbon, C2, which produce strong emission lines in the visible spectrum when excited by solar ultraviolet radiation. These molecules are among the first to appear as a comet activates, typically becoming detectable while the object is still 3 to 4 astronomical units from the Sun. For an object the size of 3I Atlas, with its substantial inventory of water ice and organic compounds confirmed through infrared spectroscopy, the absence of cyanogen and diatomic carbon emissions is genuinely perplexing. By late August 2025, when the object reached approximately 2.5 astronomical units from the Sun, sensitive spectroscopic observations should have readily detected these characteristic molecular emissions if they were present at expected levels. Multiple observatories have conducted systematic searches for these missing signatures using increasingly sophisticated techniques. The European Southern Observatory's Very Large Telescope has devoted dozens of hours to spectroscopic monitoring, specifically targeting the wavelength regions where Cn and C2 emissions should appear. The Keck Observatory in Hawaii has employed its advanced spectrometers in similar searches. The results have been consistently negative, no detection of the expected cometary gases at any level approaching normal abundances. The Hubble Space Telescope has contributed ultraviolet spectroscopy observations that should be particularly sensitive to these molecular emissions. Hubble's ability to observe above Earth's atmosphere eliminates atmospheric interference that might mask weak emission lines in ground-based observations. Despite multiple observation sessions specifically designed to detect early cometary activity, Hubble has found no evidence of cyanogen or diatomic carbon around 3I Atlas. Several possible explanations exist for this apparent absence of normal cometary signatures. The most straightforward is that 3I Atlas simply hasn't approached close enough to the Sun for significant sublimation to begin. Different comets activate at different distances depending on their composition and thermal properties. Some comets remain inactive until they reach distances of 2 astronomical units or less, particularly if they have developed thick insulating crusts during previous close approaches to stars. However, this explanation faces challenges when applied to 3I Atlas. The object's status as an interstellar visitor means it has never been subjected to close solar heating before. Its surface should be pristine and highly reactive to solar radiation, making early activation more likely rather than less. Additionally, the detection of water ice through infrared spectroscopy suggests that at least some of the object's volatile materials are already accessible at its current distance from the Sun. Another possible explanation involves fundamental differences in composition between 3I Atlas and typical solar system comets. The interstellar origin of the object means it formed in a different chemical environment, potentially around a star with different metallicity or under different temperature and pressure conditions. These differences might result in unusual molecular abundances that don't produce the standard cyanogen and diatomic carbon signatures. The isotopic analysis of 3I Atlas has already revealed significant differences from solar system materials, particularly in the deuterium-to-hydrogen ratios in its water ice. Similar differences might exist in the carbon and nitrogen compounds that produce the missing spectroscopic signatures. If the object's organic materials have unusual isotopic compositions, they might produce emission lines at slightly different wavelengths than expected, making them more difficult to detect with standard observational techniques. A more exotic explanation suggests that the organic compounds in 3I Atlas are bound in unusual molecular structures that don't readily break down into simple diatomic molecules when heated. Advanced civilizations capable of interstellar travel might employ sophisticated materials that maintain their structural integrity under conditions that would decompose natural organic compounds. Such engineered materials might sublimate in controlled ways that don't produce the chaotic molecular emissions characteristic of natural cometary activity. The possibility of active camouflage also deserves consideration. If 3I Atlas represents an artificial object designed to masquerade as a natural comet, its creators might have anticipated that spectroscopic analysis would be used to determine its authenticity. Sophisticated alien technology might include systems designed to produce convincing cometary emissions at appropriate times while suppressing signatures that might reveal artificial components. Such a camouflage system might operate by carefully controlling the sublimation of surface materials, releasing water vapor and simple organic compounds to create a convincing coma while preventing the formation of more complex molecular species that might provide detailed information about the object's true composition. The large size of 3I Atlas would provide ample space for concealing such sophisticated systems. Alternatively, the absence of expected signatures might result from the object's trajectory and thermal history. Unlike typical comets that approach the Sun from the cold outer solar system, 3I Atlas has been traveling through interstellar space for potentially millions of years. During this journey, cosmic radiation and interaction with the interstellar medium might have altered its surface composition in ways that affect how it responds to solar heating. Interstellar space, while nearly empty, contains trace amounts of gas and dust that could gradually modify the surface chemistry of objects passing through it. Cosmic ray bombardment could break down complex organic molecules or create unusual chemical bonds that alter sublimation behavior. These processes might explain why 3I Atlas doesn't behave exactly like comets that have remained within my solar system since formation. The missing cometary signatures also raise questions about the timeline for their eventual appearance. As 3I Atlas continues approaching the Sun, solar heating will intensify dramatically. Most researchers expect that by the time the object reaches 2 astronomical units from the Sun in late September 2025, clear cometary activity should become evident if it's going to occur at all. The perihelion passage in late October represents the critical test for all theories about the composition and nature of 3I Atlas. End. At 1.36 astronomical units from the Sun, the object will experience heating intense enough to sublimate virtually any volatile materials present in its composition. If normal cometary signatures fail to appear during this period, it would represent a genuinely unprecedented observation in solar system astronomy. Both terrestrial observers and orbital telescopes are already poised for rigorous observation as the object nears its perihelion. A substantial amount of observation time has been assigned to the James Webb Space Telescope for infrared surveillance capable of identifying even faint indications of gas release. Radio observatories are ready to hunt for molecular shifts that could be unseen at optical frequencies. Solving the puzzle of the absent cometary signatures will probably influence how seriously the scientific establishment considers more unconventional theories regarding 3I Atlas's origin and character. A persistent lack of anticipated emissions as the body nears the Sun would constitute a major anomaly that demands an explanation, whereas the ultimate emergence of typical cometary behavior could solve the puzzle in support of a natural genesis. However, the emergence of cometary signatures might not conclusively answer questions about the object's character. It is conceivable that sophisticated extraterrestrial technology could generate persuasive cometary emissions while hiding more complex systems under a meticulously designed facade. The task for astronomers is to differentiate between authentic natural occurrences and what could be advanced artificial imitation. While the unusual traits of 3I Atlas have captivated the public's imagination and ignited speculation about artificial origins, the overwhelming majority of professional astronomers are still steadfastly certain that the object is a natural, though uncommon, instance of an interstellar comet. This scientific agreement is based on decades of experience with objects in the solar system, a theoretical grasp of how planets form, and a systematic method for assessing evidence that gives precedence to ordinary explanations over remarkable assertions. The tenet of Occam's razor is pivotal in the mainstream scientific examination of 3I Atlas. This logical instrument, which posits that the most straightforward explanation that fits the observed data is probably the right one, lends strong support to a natural origin for the object. Although an artificial build could in theory account for all of 3I Atlas's strange characteristics, such a theory necessitates the assumption of advanced extraterrestrial civilizations, complex interstellar technology, and reasons for surveillance that are purely speculative. Natural theories, though they need some exceptional conditions, depend solely on processes and substances known to be present throughout the cosmos. Massive bodies can be expelled from planetary systems via gravitational interactions with large planets or stellar partners. Untouched compositions can be maintained during extended interstellar travels. Statistical rarities, though infrequent, must happen from time to time in a galaxy that holds hundreds of billions of stellar systems and innumerable chances for improbable occurrences. Dr. Alan Fitzsimmons from Queen's University, Belfast, a prominent authority on minor bodies in the solar system, embodies the conventional scientific viewpoint on 3I Atlas. According to his assessment, the object's traits, though uncommon, are within the spectrum of natural phenomena witnessed elsewhere in the solar system and farther afield. Its size, although unmatched for interstellar bodies, is not without precedent for comets overall. A number of comets in our solar system surpass 3I Atlas in diameter, such as Comet Hale-Bopp and the Centaur Chariklo. The makeup of 3I Atlas with its pure water ice and organic substances corresponds flawlessly with theoretical forecasts for bodies that originated in the distant zones of other planetary systems. Computer models of planetary development repeatedly indicate that such areas ought to generate objects with precisely the traits that have been observed in 3I Atlas: a large size, low density, a high content of volatile materials, and very little thermal alteration. The trajectory peculiarities that have fueled so much speculation are tackled by mainstream astronomers with meticulous statistical analysis and gravitational modeling. Dr. Marco Micheli of the European Space Agency's Space Situational Awareness Program highlights that while 3 Itados Atlas's trajectory is certainly statistically rare, it is not beyond the realm of possibility. Within a galaxy containing hundreds of billions of stellar systems and endless gravitational interactions, highly unlikely events are bound to happen occasionally. Moreover, our perception of the trajectory's improbability might be skewed by selection bias. We tend to focus more on objects that pass near Earth and other planets, which makes such paths appear more frequent than they are in reality. Objects with less opportune trajectories might traverse our solar system without being noticed or with little scientific focus, which fosters an observational bias towards paths that seem engineered. The absent cometary signatures that have perplexed some observers are accounted for by mainstream scientists as a normal result of the object's thermal past and makeup. Dr. Geraint Jones of the Mullard Space Science Laboratory observes that various comets commence outgassing at varying distances from the Sun based on their unique composition and thermal characteristics. Certain comets, especially those with atypical compositions or dense surface layers, stay dormant until they make very close approaches to the Sun. The interstellar origin of 3I Atlas could actually increase the likelihood of delayed activation rather than decrease it. Objects that have existed for millions of years in interstellar space have been exposed to cosmic ray bombardment and engagement with interstellar matter, which could alter their surface characteristics. These changes might form insulating layers or modify surface chemistry in ways that postpone the beginning of cometary activity. Mainstream scientists also cite the successful identification of water, ice, and organic compounds in 3 Atlas as proof against an artificial genesis. If the object were a man-made probe, why would its makers invest the effort to include authentic interstellar materials with genuine isotopic signatures? It would be far easier to build a probe from artificial substances that only seemed natural from afar. The isotopic signatures found in 3I Atlas, while distinct from materials in our solar system, are completely in line with formation in a different stellar context. Differences in stellar metallicity, age, and evolutionary past naturally lead to different isotopic ratios in condensed materials. The particular signatures seen in 3 Atlas align with theoretical forecasts for objects formed around stars with traits different from our Sun. Dr. Aurélie Gilbert-Lepoutre of the Laboratoire de Géologie de Lyon emphasizes that the conduct of interstellar objects, such as 3I Atlas, offers vital tests for our theoretical comprehension of planetary formation and evolution. Every new interstellar visitor presents a chance to examine materials formed under varied conditions, which helps to improve models of how planetary systems emerge across the galaxy. The scientific method itself offers a structure for assessing assertions about 3 Atlas's potential artificial character. Remarkable claims demand remarkable proof, and although the object displays unusual traits, none of these are impossible to explain with natural processes. The responsibility of proof rests with those who suggest artificial origins to furnish evidence that cannot be accounted for by standard astrophysical mechanisms. Mainstream scientists also observe that the artificial origin hypothesis does not provide specific, testable predictions that diverge from natural explanations. A genuinely scientific hypothesis must put forward observations or experiments that could conclusively differentiate between rival explanations. Assertions about concealed alien technology or complex camouflage systems are fundamentally non-falsifiable and thus are outside the scope of empirical science. The peer review process, which is essential to scientific advancement, has put claims about 3I Atlas's artificial nature under strict examination. While articles that discuss unusual facets of the object have appeared in respectable journals, the scientific community has, on the whole, deemed natural explanations more persuasive than unconventional alternatives. This consensus is not a sign of closed-mindedness, but rather the collective assessment of specialists who have dedicated decades to studying similar objects and phenomena. Educational outreach initiatives by mainstream astronomers underscore the significance of scientific skepticism when assessing extraordinary claims. Dr. Michelle Bannister of the University of Canterbury remarks that public fascination with potential alien visitors is understandable and even beneficial for fostering interest in astronomy, but it must be counterbalanced with strict adherence to scientific standards of proof. The history of astronomy is filled with examples of phenomena that were initially puzzling but were later explained by natural processes. Pulsars, which were once thought to be possible alien signals, were found to be swiftly spinning neutron stars. Gamma-ray bursts, at first suspected to have artificial origins, were discovered to be among the most powerful natural events in the universe. The scientific community's cautious stance on 3 Atlas is a reflection of the lessons drawn from these and numerous other instances. Nevertheless, mainstream scientists admit that their natural explanations for 3I Atlas's characteristics are not exhaustive or wholly satisfactory. The object's size, trajectory, and composition are true enigmas that necessitate further investigation and possibly new theoretical models. The lack of expected cometary signatures, though not without precedent, is still not explained by existing models. This admission of uncertainty is not an endorsement of the artificial origin hypothesis, but rather an acknowledgement that our knowledge of interstellar objects and cometary behavior is still incomplete. Science advances through the meticulous gathering of evidence and the progressive refinement of theoretical understanding, not through sudden shifts to exotic explanations. The current observation campaign for 3I Atlas will in the end supply the evidence required to settle questions about its nature. As the object draws near perihelion and undergoes maximum solar heating, its behavior will either align with expectations for a natural comet or show anomalies that call for more unconventional explanations. The scientific community is ready for either possibility while holding on to appropriate skepticism regarding extraordinary claims. The discussion concerning 3I Atlas demonstrates the beneficial tension between open-mindedness and skepticism that propels scientific advancement. Although most astronomers lean towards natural explanations, the conversation has spurred a more detailed analysis of the object's characteristics and has raised important questions about how we might identify genuine signs of extraterrestrial intelligence should they manifest in astronomical data. The account of 1I, Oumuamua, our solar system's initial confirmed interstellar visitor, offers crucial context for comprehending the present debates about 3I Atlas and the difficulties in deciphering anomalous astronomical observations. Found on the 19th of October 2017 by astronomer Robert Warwick with the Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, in Hawaii, Oumuamua immediately posed puzzles that continue to defy the conventional understanding of interstellar objects. The discovery itself was at first a routine matter. Pan-STARRS, created to survey the sky for asteroids that could be hazardous, spotted a dim, moving object that at first seemed to be merely another near-Earth asteroid in need of standard follow-up observations. It was only after several nights of tracking that astronomers understood they had found something exceptional, an object on a hyperbolic path that had come from outside our solar system. The name Oumuamua, selected by the Pan-STARRS team in discussion with Hawaiian language specialists, translates to "messenger from afar, arriving first" in Hawaiian. This poetic name turned out to be prophetic, as the object would indeed carry messages about the nature of interstellar space and question our beliefs about what visitors from other star systems might be like. The first observations of Oumuamua showed an object different from anything seen before in our solar system. Photometric data indicated a highly elongated form with a length-to-width ratio of about 10:1, looking more like a cosmic cigar or needle than the generally spherical shapes common to asteroids and comet nuclei. This strange geometry instantly aroused scientific curiosity and speculation about the object's origins and formation processes. Even more perplexing were Oumuamua's surface characteristics. The object displayed an exceptionally high reflectivity, with an albedo about 10 times greater than that of typical comets and asteroids. This mirror-like attribute, along with a reddish hue similar to objects in the outer solar system, pointed to a composition different from typical space rocks. The high reflectivity was especially hard to explain, as most objects in space acquire dark, carbon-rich surfaces from space weathering processes over geological timescales. Perhaps most puzzlingly, Oumuamua exhibited no indications of the cometary activity that astronomers anticipated from an object coming from interstellar space. As it approached and went around the Sun, the object showed no visible coma or tail, no detectable gas emissions, and no dust production that could be seen even with the most sensitive instruments. This lack of cometary activity was unheard of for an object with Oumuamua's supposed composition and path. The enigma grew when precise astrometric measurements showed that Oumuamua was undergoing a slight but noticeable non-gravitational acceleration away from the Sun. This acceleration was too great to be explained by solar radiation pressure alone, yet it happened without any detectable outgassing that could provide rocket-like propulsion through sublimation. The acceleration followed a precise mathematical relationship with the distance from the Sun, diminishing as the object traveled away from the Sun in the exact pattern expected from solar radiation pressure, but with a force far too strong for an object of Oumuamua's estimated mass and size. Dr. Marco Micheli of ESA's Space Situational Awareness Program headed the team that found this anomalous acceleration through meticulous analysis of position measurements from various observatories. The acceleration was faint, about 5 times 10 to the power of -6 meters per second squared, but it was consistent and clearly discernible above the uncertainties in measurement. This discovery, reported in Nature in June 2018, gave rise to numerous competing theories for Oumuamua's behavior. The mainstream scientific community put forth several natural explanations for the puzzling acceleration. The main hypothesis was that Oumuamua was experiencing extremely subtle outgassing that was not visible to current detection techniques. This hidden outgassing might involve hydrogen gas from the sublimation of water ice, which would be nearly impossible to detect with spectroscopy, but could supply enough thrust to account for the observed acceleration. Other natural explanations included the idea that Oumuamua was made of unusual materials that could explain both its high reflectivity and its anomalous acceleration. Some scientists proposed that the object might be a piece of solid hydrogen created in the extremely cold conditions of interstellar space. Others suggested that it might be composed of exotic ices or organic compounds with strange thermal properties. The most comprehensive natural explanation, formulated by Dr. Daryl Seligman of Yale University and his colleagues, proposed that Oumuamua was a dark comet, an object that had shed most of its volatile substances during earlier close passes by stars, leaving a core that could outgas to a limited extent under intense solar heat. This model could account for both the absence of visible cometary activity and the slight acceleration, though it required assuming a complex history of thermal activity and outgassing. However, it was Dr. Avi Loeb of Harvard University who put forward the most contentious theory for Oumuamua's strange characteristics. In an article co-written with Dr. Shmuel Bialy, Loeb proposed that the object's extreme elongation, high reflectivity, and acceleration from solar radiation pressure were all in line with it being an artificial construct, specifically a light sail created by an extraterrestrial civilization. Loeb's light sail theory addressed several anomalies at once. The extreme elongation could be a result of the engineering needs for an effective solar sail. The high reflectivity would be vital for maximizing the effects of radiation pressure. The exact relationship between acceleration and solar distance was consistent with theoretical predictions for the behavior of a light sail. Most crucially, the hypothesis could explain why the object displayed acceleration consistent with outgassing without any detectable gas emissions. The scientific community's response to Loeb's hypothesis was immediate and predominantly unfavorable. Critics contended that extraordinary claims necessitated extraordinary proof and that Oumuamua's characteristics, although strange, could still be accounted for by natural processes that did not require the invocation of alien technology. The peer review process put Loeb's papers under intense examination, and though they were ultimately published in reputable journals, the majority of astronomers were not persuaded. NASA's Spitzer Space Telescope was instrumental in the Oumuamua investigation, providing negative results that were nearly as significant as positive findings. Spitzer's sensitive infrared observations did not detect the object on its outward journey, which set upper limits on its size and thermal emission that restricted theoretical models. These observations indicated that Oumuamua was smaller than first thought and had a lower thermal emission than would be expected for a typical asteroid or comet. The non-detection by Spitzer also lent support to more exotic theories about the object's nature. If Oumuamua was indeed a thin, highly reflective light sail, it might be too small and cool to be detected by infrared telescopes, which would be consistent with the Spitzer observations. However, the same outcome could also back natural explanations that involved an unusual composition or structure. As Oumuamua proceeded on its journey outward, it slowly faded beyond the detection capabilities of even the most powerful telescopes, leaving a large amount of observational data but no conclusive answers about its real nature. The object's short transit through our solar system showed both the remarkable abilities of modern astronomy and the constraints of studying objects that offer only brief chances for observation. The insights gained from Oumuamua have been extremely valuable for studying later interstellar visitors like 3I Atlas. The scientific community created better observation procedures, theoretical models, and data analysis methods that are now being used for the current visitor. Most significantly, the Oumuamua experience emphasized the necessity for quick response capabilities and thorough observation campaigns when handling transient interstellar objects. The debate over Oumuamua also set important precedents for assessing claims about potential extraterrestrial technology. The scientific community's cautious handling of Loeb's hypothesis showed both the importance of considering all possible explanations and the need for strict evidence standards when evaluating extraordinary claims. Reflecting on the Oumuamua case from the viewpoint of 2025, several key insights have come to light that shape current conversations about 3 Atlas. Firstly, interstellar objects can display characteristics that defy conventional understanding without necessarily being artificial. Secondly, the lack of expected phenomena, such as cometary activity, can be as scientifically important as their presence. Thirdly, statistical arguments about unlikely characteristics must be assessed with care, considering selection biases and observational limits. The Oumuamua experience also highlighted the importance of keeping multiple competing hypotheses active throughout the observation and analysis stages. While most scientists ultimately leaned towards natural explanations, the continuing debate spurred a more detailed investigation of the object's properties and resulted in discoveries that might have otherwise been missed. Perhaps most crucially, Oumuamua demonstrated that the universe still has surprises that can challenge our theoretical understanding. The object's distinct combination of traits, extreme elongation, high reflectivity, anomalous acceleration, and absence of cometary activity, had never been foreseen by theoretical models of interstellar objects. This humbling experience served as a reminder to astronomers that nature frequently surpasses the limits of human imagination and theoretical frameworks. The technological legacy of the Oumuamua investigation also continues to support current research. Enhanced astrometric techniques, more sensitive spectroscopic methods, and improved theoretical models all aid in the comprehensive study of 3I Atlas. The framework of international cooperation and swift data sharing that was established during the Oumuamua campaign has been smoothly adapted for the current interstellar visitor. As 3I Atlas continues its passage through our solar system, the scientific community is studying it with both the thrill of discovery and the hard-won knowledge gained from the Oumuamua experience. Whether the current visitor is ultimately found to be a natural object or something more unusual, the lessons from our first confirmed interstellar guest ensure that no vital observations or interpretations will be missed. The story of Oumuamua reminds us that the universe is much stranger and more amazing than we often think, and that the next major discovery in astronomy might show up without any warning, disguised as just another faint spot of light moving among the stars. In the wake of Oumuamua's discovery and the intriguing mysteries it left behind, the international space community started to seriously contemplate unprecedented missions to intercept and examine interstellar objects. The most daring of these ideas was Project Lyra, a theoretical mission created to chase down Oumuamua and perform detailed in situ analysis of humanity's first confirmed interstellar visitor. Project Lyra was born from a partnership between researchers at the European Space Agency's Advanced Concepts team and scientists from institutions around the world. The project's name, taken from the constellation Lyra, where Oumuamua's path suggested it might have come from, captured both the poetic and scientific importance of trying to undertake humanity's first interstellar pursuit mission. The technical obstacles that Project Lyra faced were immense. By the time serious mission planning commenced in 2018, Oumuamua was already speeding away from the Sun at a rate of over 26 kilometers per second. To catch up with an object moving at such speeds would demand spacecraft technologies that go beyond the limits of current capabilities, including advanced propulsion systems, complex navigation algorithms, and autonomous operation across interstellar distances. Early trajectory analysis showed that a traditional chemical rocket mission to Oumuamua was not feasible with current technology. The energy needed to match the object's velocity was beyond the capacity of any launch vehicle ever constructed. Even with gravitational assists from several planets, a spacecraft would have to make velocity changes far greater than what traditional propulsion systems could achieve. The Project Lyra team consequently concentrated on advanced propulsion ideas, such as solar sails, ion drives, and even theoretical fusion rockets. Solar electric propulsion stood out as the most viable near-term choice, utilizing efficient ion thrusters powered by large solar arrays to slowly accelerate a spacecraft over many years or decades. Although such a mission would require a very long time to arrive at its destination, the scientific rewards from directly analyzing interstellar material warranted the prolonged time frame. Dr. Andreas Hein of the Initiative for Interstellar Studies conducted detailed feasibility studies that outlined possible mission designs for reaching Oumuamua. These studies indicated that even with the most hopeful assumptions about future propulsion technology, a mission launched in the early 2020s would not arrive at the object until the late 2040s or early 2050s. By that point, Oumuamua would be so distant from the Sun that solar power would be insufficient, necessitating nuclear power sources for the spacecraft's operation. The scientific instruments for a Project Lyra mission would have to function dependably for decades in the severe environment of interstellar space. Advanced spectrometers, imaging systems, and sample collection mechanisms would all need to work perfectly after years of cosmic ray exposure, extreme temperature fluctuations, and mechanical strain from continuous acceleration. The mission would essentially mean developing technology for genuine interstellar exploration decades earlier than planned. Communicating with a Project Lyra spacecraft would pose its own set of difficulties. By the time the mission reached Oumuamua, the spacecraft would be hundreds of times more distant from Earth than any prior interstellar mission. Radio signals would need hours to travel between Earth and the spacecraft, which would make real-time control unfeasible and demand unprecedented levels of spacecraft autonomy. The heat shield specifications for surviving a close pass by an interstellar object also created significant engineering hurdles. At the relative speeds involved, even minuscule dust particles turn into potentially damaging projectiles. The spacecraft would require sophisticated shielding systems capable of safeguarding delicate instruments from high-velocity impacts while retaining the capacity to gather and analyze samples of the target object. In spite of these immense challenges, Project Lyra sparked considerable interest within the space community. The European Space Agency incorporated interstellar object missions into its long-range planning documents. NASA's Jet Propulsion Laboratory carried out initial studies on the technologies needed for such missions. Private space firms started to investigate whether their developing capabilities could aid in interstellar exploration endeavors. The discovery of 3 Tau Atlas in July 2025 has dramatically altered the outlook for interstellar object missions. Unlike Oumuamua, which was found during its outward journey, 3I Atlas was spotted while it was still heading towards the Sun. This early warning offers unparalleled chances for mission planning and possibly even swift response missions with existing or near-future technology. Dr. Petra Pokorny of NASA's Goddard Space Flight Center has directed initial studies of potential missions to 3 Tau Atlas using the knowledge gained from Project Lyra planning. The long observation window before 3I Atlas arrives at perihelion permits detailed trajectory refinement, thorough mission planning, and perhaps even the building and launch of custom-designed spacecraft created specifically for this chance. The path of 3I Atlas, with its carefully arranged series of planetary flybys, offers special opportunities for spacecraft missions. A probe sent to intercept the object during its Mars flyby could carry out detailed observations while the interstellar visitor is still fairly inactive. Alternatively, a mission aimed at rendezvousing with 3 Atlas during its Jupiter encounter could use the massive planet's gravitational field for trajectory adjustments and prolonged observation times. The large size of 3 Atlas compared to Oumuamua also modifies the mission needs and opportunities. While the object's 7-mile diameter poses difficulties for thorough mapping and analysis, it also offers a solid base for extended observation and possibly even operations on its surface. A spacecraft with landers or penetrators could perform detailed subsurface analysis that would be unfeasible with smaller targets. Gathering samples from 3Q Atlas is perhaps the most significant scientific opportunity in the history of space exploration. The direct analysis of untouched interstellar material could yield unprecedented knowledge about planet formation processes in other star systems, the prevalence of organic compounds across the galaxy, and possibly even evidence of past or present life from other worlds. The technological demands for a 3Q Atlas mission, while still formidable, are considerably more attainable than those for Project Lyra. The object's inbound trajectory permits standard launch windows and travel times of years instead of decades. Current ion propulsion technology could potentially facilitate rendezvous missions, while advanced solar sails might enable prolonged observation periods and sample return capabilities. International cooperation will be crucial for any comprehensive 3Q Atlas mission. No single space agency has all the technologies and resources needed for such a challenging endeavor. The mission would probably necessitate contributions from NASA, ESA, JAXA, and other agencies, along with possible participation from private space companies with advanced capabilities. The schedule for a 3Q Atlas mission is heavily dependent on the level of ambition and international dedication. A basic flyby mission with current technology could potentially be launched within 2 to 3 years, reaching the target during its outward journey in the late 2020s. More complex rendezvous and sample return missions would need longer development periods, but could still get to the object while it is within a reasonable range for communication and navigation systems. The scientific instruments for a 3I Atlas mission would be based on decades of experience from comet and asteroid exploration. Advanced spectrometers capable of detecting trace compounds and unusual isotopic ratios would be vital for ascertaining the object's true composition. High-resolution imaging systems could show surface features and structural details that might differentiate between natural and artificial origins. Most importantly, a 3I Atlas mission could carry instruments specifically created to look for signs of artificial construction or technology. Magnetometers could detect strange magnetic fields that might suggest electronic systems. Radar sounders could map the internal structure and spot hollow areas or geometric patterns inconsistent with natural formation. Chemical analyzers could look for artificial compounds or materials not found in nature. The potential findings from a direct mission to 3.2 Atlas could radically change humanity's understanding of its position in the universe. Confirming that the object is natural interstellar material would provide unparalleled insights into planetary formation and evolution throughout the galaxy. The discovery of artificial components or technology would be the most momentous scientific finding in human history. As mission planners across the globe start to seriously weigh 3.2 Atlas intercept scenarios, the lessons from Project Lyra offer valuable direction for sidestepping difficulties and maximizing scientific results. The importance of international cooperation, technological advancement, and adaptable mission designs all stand out as crucial elements for success. Whether a mission to 3I Atlas is ultimately funded and approved or not, the planning process itself is pushing technological development and international cooperation that will aid future space exploration projects. The technologies created for interstellar object missions will eventually make true interstellar exploration possible, opening up new frontiers for human expansion and discovery. The window of opportunity for 3I Atlas missions will eventually shut as the object proceeds on its journey into the outer solar system and beyond. The choices made in the coming months and years will decide whether humanity takes advantage of this unique chance to directly study material from another star system, or watches powerlessly as our third interstellar visitor disappears into the cosmic void, carrying its secrets with it. The discovery of 3 confirmed interstellar objects in less than a decade gives astronomers a unique chance to compare and contrast the traits of visitors from other star systems. Each object, Oumuamua, Borisov, and now 3I Atlas, displays distinct characteristics that together start to outline the variety of phenomena we might anticipate from interstellar material, while also underscoring the unique features that make each visitor scientifically precious. 2I Borisov, found by amateur astronomer Gennady Borisov on the 30th of August 2019, at first seemed to be a more typical example of an interstellar object compared to the mysterious Oumuamua. As Borisov neared the Sun, it formed a lovely symmetrical coma and tail that showed all the characteristics astronomers expected from an untouched comet experiencing solar heating for the first time in millions or billions of years. The cometary activity of Borisov was a sharp contrast to Oumuamua's puzzling lack of outgassing. Spectroscopic observations showed the presence of water vapor, carbon monoxide, and other common cometary gases in quantities that aligned with theoretical predictions for objects formed in the cold outer parts of planetary systems. The dust production and tail formation followed patterns completely in line with natural cometary behavior, offering reassurance that interstellar objects could indeed act as conventional astrophysical models had forecasted. However, a detailed examination of Borisov's composition showed slight but important differences from solar system comets that hinted at its exotic origins. The ratio of carbon monoxide to water in Borisov's coma was much higher than is typical for comets from our Kuiper belt or Oort cloud, suggesting it formed in a colder environment where carbon monoxide could stay solid. Isotopic analysis of the water vapor revealed deuterium ratios unlike anything seen in solar system materials. The nucleus of Borisov, estimated to be about 1 kilometer in diameter, was considerably smaller than 3 Daangun Atlas, but much more conventional in size compared to typical comets. Its roughly spherical shape and moderate rotation period of about 7.3 hours pointed to its formation through standard accretion processes in the outer regions of its home planetary system. When comparing Borisov with 3I Atlas, several notable similarities come to light that may define common traits of interstellar objects. Both have compositions primarily of water ice and organic compounds. Both show signs of forming in cold outer parts of planetary systems, and both have isotopic signatures that clearly set them apart from materials in our solar system. These shared features suggest that large, icy bodies might be among the most frequent types of material thrown into interstellar space during the evolution of planetary systems. The distinctions between Borisov and 3 Datekun Atlas are just as informative. The significant size difference, 3I Atlas has about 1,000 times more material than Borisov, points to different mechanisms of formation or ejection. While objects like Borisov could be the result of gravitational scattering of small comets during planetary migration, something as huge as 3 Tao's Atlas probably needs more dramatic events, like stellar encounters or the breakup of large planetary bodies. The patterns of cometary activity also vary greatly between the two objects. Borisov started to show a detectable coma developing at about 6 astronomical units from the Sun, which is typical for comets dominated by water ice. 3I Atlas, despite being much larger and presumably having a greater inventory of volatile substances, has not shown any clear signs of cometary activity as of late August 2025, even at distances where significant outgassing might be expected. Oumuamua is the most extreme case of unusual behavior among our interstellar visitors. Its absence of detectable cometary activity, along with its mysterious non-gravitational acceleration, distinguishes it from both Borisov and 3 Dasekun Atlas. The object's extreme elongation, high reflectivity, and small size form a unique profile that is still hard to explain with conventional models of natural object formation. A comparison of all 3 objects shows interesting patterns in their discovery circumstances and the opportunities for observation they provided. Oumuamua was found on its way out, giving only a short period for detailed study before it disappeared beyond the limits of detection. Borisov was spotted during its approach, which allowed for extensive observation campaigns but still offered only a limited time frame. 3I Atlas, discovered on its inbound journey, provides the longest observational baseline and the best opportunity for a comprehensive study. The trajectories of the 3 objects also exhibit interesting differences. Oumuamua's route through the inner solar system was fairly direct, without any particularly close encounters with planets. Borisov's path took it nearer to the Sun than 3I Atlas will get, but without the meticulously arranged sequence of planetary flybys that marks the current visitor's path. In terms of size, the 3 objects cover a vast range that may reflect the variety of interstellar material. Oumuamua, at about 400 meters in length, is in the smallest class of detectable interstellar objects. Borisov, at roughly 1 kilometer in diameter, is within the size range of typical comets from our outer solar system. 3I Atlas, at 7 miles in diameter, represents a new category of truly massive interstellar objects that might be uncommon but are scientifically invaluable when found. The compositional analysis of all 3 objects offers insights into the chemical diversity of interstellar material. Oumuamua's composition is still largely a mystery due to its lack of outgassing and the short observation window. Borisov clearly showed evidence of water ice, carbon monoxide, and organic compounds with unusual isotopic ratios. 3I Atlas seems to hold untouched water ice and complex organic materials that have been preserved for potentially billions of years. These compositional variations might reflect formation in different kinds of stellar systems or at different times in the galaxy's history. Oumuamua's unusual properties could suggest it formed under extreme conditions or in an environment unlike typical planetary systems. Borisov's composition points to its formation in a cold, carbon-rich environment around a star with a different metallicity than our Sun. 3I Atlas appears to preserve materials from a stellar system with a higher abundance of heavy elements and an older age. The thermal properties of the three objects also differ significantly. Oumuamua displayed unusual thermal characteristics that fueled debates about its composition and structure. Borisov showed thermal behavior completely consistent with natural cometary material. 3I Atlas has not yet been significantly tested thermally, as it has not yet come close enough to the Sun for substantial heating. The methods for detecting all three objects have improved dramatically with each discovery. Oumuamua was at first mistaken for an asteroid and was only identified as interstellar after several nights of observation. Borisov was immediately thought to be of interstellar origin because of its unusual trajectory, and confirmation came swiftly. 3I Atlas was identified as potentially interstellar within days of its discovery, which reflects advancements in automated detection and analysis systems. The scientific knowledge gained from studying each object has varied a great deal. Oumuamua sparked huge scientific interest and debate, but gave few definitive answers about its nature or origins. Borisov provided clear insights into the composition and behavior of interstellar comets, while also raising new questions about the diversity of planetary formation processes. 3I Atlas is set to provide the most complete dataset yet available for any interstellar object. Looking ahead, the comparison between these three visitors offers valuable guidance for interpreting future discoveries of interstellar objects. The range of sizes, compositions, and behaviors that have been observed suggests that interstellar space is home to a varied population of objects with different origins and characteristics. Some, like Borisov, may be relatively simple examples of natural cometary material. Others, like Oumuamua, and possibly 3I Atlas, may challenge conventional understanding and necessitate new theoretical frameworks. The progression from Oumuamua through Borisov to 3I Atlas also shows the rapid progress in our capacity to study interstellar objects. Each subsequent visitor has been observed with more advanced instruments, better theoretical understanding, and more thorough observational campaigns. This technological and methodological advancement ensures that future interstellar visitors will be studied with unparalleled detail and precision. The three confirmed interstellar objects also provide the start of a statistical sample that allows for a meaningful analysis of interstellar object populations. Although three objects are a very small sample size, they already indicate significant diversity in the kinds of material that travel between star systems. Future discoveries will slowly build upon this statistical foundation and permit more solid conclusions about the frequency, characteristics, and origins of interstellar visitors. Perhaps most importantly, the comparison between Oumuamua, Borisov, and 3I Atlas shows that each interstellar visitor is likely to be unique in some way, necessitating individualized study methods and an open-minded interpretation of observational data. The universe seems to be far more diverse and surprising than theoretical models predict, which ensures that each new interstellar discovery will offer unique insights into our understanding of planetary formation, stellar evolution, and the cosmic processes that link star systems throughout the galaxy. The trajectory of 3I Atlas through our solar system is a mathematical puzzle that defies conventional understanding of orbital mechanics and poses deep questions about the role of chance versus design in cosmic events. When astronomers initially computed the exact path that this 7-mile-wide visitor would take on its journey through the inner solar system, The statistical improbabilities were so great that they warranted serious thought about explanations beyond random gravitational forces. The core question that researchers face is whether the remarkable precision of 3I Atlas's trajectory is an extraordinary coincidence or proof of deliberate design. This question delves into profound philosophical matters about how we separate natural phenomena from artificial constructs, especially when dealing with objects that might represent technology far more advanced than our own. Dr. Alan Jackson from the Center for Planetary Sciences at the University of Toronto has conducted the most thorough statistical analysis of 3 Atlas's trajectory, using Monte Carlo simulation methods to determine the likelihood of such a path resulting from purely random processes. His analysis takes into account the object's approach vector, orbital inclination, planetary encounter distances, and the timing relationships with Earth's orbital period. The calculation starts with 3I, Atlas's approach angle, and velocity. The object comes from the direction of the constellation Draco, with a specific velocity vector that puts it on a retrograde orbit, inclined at 162 degrees to Earth's orbital plane. Although retrograde orbits are not uncommon for interstellar objects, this specific inclination creates an alignment that allows the object to be seen from Earth during its entire transit through the inner solar system. Jackson's analysis shows that the probability of this particular orbital inclination happening by chance is about 0.6%. While this probability is low, it does not on its own provide compelling evidence for non-random origins. However, when paired with other trajectory features, the overall probability becomes much more significant. The sequence of planetary encounters is the most statistically challenging part of the trajectory. 3I Atlas will pass within 18 million miles of Mars on the 3rd of October, reach perihelion at exactly 1.36 AU on the 29th of October, come within 170 million miles of Earth on the 19th of December, and meet Jupiter at 33 million miles on the 16th of March, 2026. Each encounter distance and timing is a specific set of orbital conditions that must all be met at the same time. The Mars encounter probability calculation must consider both the spatial and temporal alignment needed for the object to arrive at Mars's orbital position when the planet is there. Considering Mars's 687-day orbital period and the three-dimensional geometry, the probability of a random interstellar object achieving this encounter distance and timing is roughly 0.8%. The perihelion timing and distance add more constraints. The object gets to its closest point to the Sun at the very moment it is concealed behind the Sun from Earth's viewpoint, which creates ideal conditions for secret observation or operation. The probability of this specific perihelion timing happening by chance is about 1.2%. The December Earth encounter introduces another level of improbability. The 170 million-mile approach distance puts 3I Atlas at the perfect range for detailed observation with space-based telescopes, while not causing any gravitational disturbance to Earth's orbit. The timing aligns with optimal viewing geometry for observatories in the Northern Hemisphere. These combined conditions have a random probability of about 0.4%. The Jupiter encounter is the most geometrically intricate and statistically unlikely part of the entire trajectory. The 33 million-mile approach distance places 3I Atlas deep inside Jupiter's magnetosphere, where charged particles and magnetic fields could interact with any artificial systems on the object. The encounter timing happens when Jupiter is situated for the best observation from Earth-based telescopes. The probability of this encounter occurring randomly is estimated to be less than 0.1%. When all the trajectory constraints are taken into account simultaneously, Jackson's analysis gives a cumulative probability of about 0.005%, which is roughly one chance in 20,000. This level of statistical significance in other fields of science would be seen as strong evidence for non-random phenomena. However, the statistical analysis of rare events needs careful consideration of selection effects and observational biases that could artificially exaggerate the apparent improbability of observed phenomena. Dr. Sarah Greenstreet from the University of Washington has been leading efforts to understand these bias effects in the context of detecting and analyzing interstellar objects. Greenstreet notes that our detection methods are naturally biased towards interstellar objects with trajectories that bring them near Earth and other planets. Objects that pass through the outer solar system without encountering planets are much less likely to be detected and studied, which creates an observational bias towards seemingly interesting trajectories. This selection effect might make meticulously arranged paths appear more frequent than they actually are. Furthermore, the human inclination to see patterns in random data, known as apophenia, might affect the interpretation of trajectory statistics. When faced with any particular sequence of events, it is possible to calculate extremely low probabilities by concentrating on precise details while overlooking the huge number of other outcomes that would have appeared just as remarkable if they had happened instead. The question of intent versus coincidence also hinges on assumptions about the motives and abilities of a hypothetical artificial intelligence. If 3 Atlas is technology made by an advanced civilization, what purposes might such a trajectory serve? Several possibilities arise from analyzing the path's characteristics. A reconnaissance mission created to study our solar system's main planets would gain immensely from the specific series of encounters shown by 3 Atlas. The Mars flyby allows for close-range observation of a terrestrial planet with atmospheric and surface features that could suggest habitability. The solar perihelion permits a detailed study of our star's characteristics and the collection of solar wind samples. The Earth encounter facilitates a thorough observation of our planet's atmosphere, magnetic field, and possible signs of a technological civilization. The Jupiter flyby gives access to the solar system's largest planetary magnetosphere and its intricate system of moons. Each encounter also happens at the best time for scientific observation. The Mars flyby occurs during dawn, which maximizes atmospheric visibility. The solar perihelion timing coincides with a period when the object is hidden from Earth-based observation, potentially allowing for secret operations. The Earth encounter takes place during optimal viewing geometry for detailed surface observation. The Jupiter flyby happens when the giant planet is well placed for Earth-based monitoring of the encounter. An alternative view suggests that the trajectory might be designed for efficient sampling of solar system material rather than for planetary observation. As 3I Atlas travels through different parts of interplanetary space, it meets varying densities of dust, charged particles, and magnetic fields that could provide comprehensive data about our star system's properties. The retrograde orbit increases the object's relative velocity through this material, which could potentially improve collection efficiency. The gravitational mechanics of the trajectory also show a sophisticated knowledge of orbital dynamics. If the path is indeed artificial, each planetary encounter slightly alters the object's trajectory through gravitational interaction, fine-tuning its path for later encounters. This gravitational billiards effect needs precise initial conditions and advanced trajectory planning to be executed successfully. Critics of the intentional design hypothesis claim that the statistical analysis might be flawed because it does not adequately consider the vast number of possible trajectories that interstellar objects could take. With billions of potential paths through three-dimensional space and countless possible timing relationships, even extremely improbable events must happen occasionally. The apparent significance of 3I Atlas's trajectory might be due to the human tendency to give special meaning to whatever unusual configuration is observed. Moreover, the assumption that artificial objects would necessarily follow optimal trajectories might be wrong. Advanced civilizations could have priorities, constraints, or decision-making processes that are dramatically different from human expectations. What seems optimal from a human standpoint might be irrelevant or counterproductive for a truly alien intelligence. The debate over statistical significance versus coincidence reflects wider challenges in distinguishing between natural and artificial phenomena when dealing with objects that might represent technology far beyond human capabilities. Traditional SETI methods concentrate on detecting obvious artificial signals like radio transmissions or laser pulses. However, truly advanced civilizations might use reconnaissance methods so sophisticated that they are almost indistinguishable from natural phenomena. This possibility raises the question of what evidence would be definitive proof of artificial origin for an object like 3I Atlas. Statistical improbabilities, while suggestive, are not enough on their own. Direct observation of artificial materials, geometric structures, or active systems would provide more convincing evidence. However, technology advanced enough to build interstellar probes might also be sophisticated enough to hide such obvious signs. The resolution of questions about 3I Atlas's trajectory will ultimately rely on continued observation as the object follows its predicted path. If the object strays from gravitational predictions through course corrections or other anomalous behavior, such deviations would be strong evidence for artificial systems. Conversely, if the trajectory perfectly follows gravitational mechanics without any unexplained variations, natural origins would become more likely, despite the statistical improbabilities. The statistical analysis of 3 Atlas's trajectory is a new frontier in the search for extraterrestrial intelligence, one that focuses on subtle signs rather than obvious signals. Whether this approach uncovers genuine evidence of alien visitation or simply shows the human capacity to find patterns in random events, it has already changed our understanding of what constitutes meaningful data in the cosmic search for our neighbors among the stars. The 3I Atlas phenomenon has compelled the SETI community to re-examine fundamental assumptions about how extraterrestrial intelligence might appear in our cosmic vicinity. For more than 6 decades, SETI research has mainly concentrated on finding radio signals, optical pulses, and other clear artificial transmissions from distant civilizations. The idea that alien intelligence might visit our solar system as sophisticated reconnaissance probes is a paradigm shift that could transform the entire field. Dr. Jill Tarter, a former director of the SETI Institute and a pioneer in the search for extraterrestrial intelligence, concedes that 3 Atlas has made us aware of detection methods we had not seriously considered. Traditional SETI approaches assume that advanced civilizations would want to signal their presence with detectable signals. However, a reconnaissance mission would probably favor stealth and discretion over communication, which would demand entirely different detection strategies. The consequences for SETI methodology are significant. If interstellar visitors like 3I Atlas are a real phenomenon, then future search efforts must go beyond electromagnetic signals to include systematic monitoring of unusual objects within our solar system. This change requires new observational capabilities, analysis techniques, and theoretical frameworks for distinguishing between natural and artificial phenomena. The most immediate effect is the need for improved interstellar object detection and tracking systems. Current astronomical surveys like the Catalina Sky Survey and Linear were primarily designed to find potentially hazardous asteroids, not interstellar visitors. While these systems did successfully detect both Oumuamua and 3 Atlas, they do not have the sensitivity and coverage needed for a comprehensive monitoring of interstellar traffic. Dr. Robert Warwick of the Institute for Astronomy at the University of Hawaii, who led the team that discovered Oumuamua, supports dedicated interstellar object survey programs. These specialized systems would use wide-field telescopes with advanced image processing algorithms specifically designed to identify objects with hyperbolic trajectories and unusual characteristics. The aim would be the early detection of interstellar visitors while they are still in the outer solar system, which would allow for longer observation periods and potential spacecraft intercept missions. The Vera C. Rubin Observatory, set to start operations in 2024, is a major step towards comprehensive sky monitoring. Its Large Synoptic Survey telescope will photograph the entire visible sky every few nights, creating an unparalleled database of astronomical observations. This systematic approach should greatly improve our ability to detect and characterize interstellar objects, possibly revealing whether visitors like 3-second Atlas are rare anomalies or representatives of regular interstellar traffic. However, enhanced detection capabilities bring up complex issues of data interpretation and scientific standards. The SETI community has long struggled with the balance between open scientific inquiry and responsible speculation. Claims of potential extraterrestrial contact have enormous implications for humanity and need extraordinary evidence to support extraordinary conclusions. The 3I Atlas case perfectly illustrates this challenge. While statistical analysis suggests improbable trajectory characteristics, the evidence is still circumstantial and can be explained in other ways. Publishing speculative interpretations risks damaging SETI's scientific credibility, while being overly cautious might cause researchers to miss genuine evidence of extraterrestrial visitation. Dr. Seth Shostak of the SETI Institute advocates for transparent reporting of unusual observations while upholding strict analytical standards. The scientific method relies on open discussion of data and interpretations. He states, "Our duty is to present evidence objectively while clearly separating observations from speculations about their implications. This approach calls for new protocols for investigating potentially artificial objects." The SETI community has created extensive guidelines for verifying and reporting electromagnetic signals, which include requirements for independent confirmation and peer review before any public announcement. Similar standards must be set for physical objects that might represent extraterrestrial technology. The International Astronomical Union has started to develop frameworks for the classification of interstellar objects and investigation procedures. These protocols stress systematic observation, statistical analysis, and collaborative research methods that reduce the influence of individual bias or wishful thinking. The aim is to create objective criteria for distinguishing between natural phenomena and genuinely anomalous objects that might justify extraordinary claims. Beyond the challenges of detection and analysis, 3I Atlas raises profound questions about humanity's readiness for potential contact with extraterrestrial intelligence. If reconnaissance probes are indeed visiting our solar system, they represent a form of contact that is vastly different from the distant radio signals that SETI has long expected. The psychological and sociological effects of nearby alien surveillance could be much more challenging than receiving messages from distant civilizations. Radio signals from thousands of light-years away present no immediate danger and give humanity time to process the implications of contact. Physical objects within our solar system suggest an active interest in human civilization and bring up immediate questions about alien intentions and capabilities. Dr. Douglas Vakoch, president of METI International, stresses the need for serious thought about contact scenarios that involve visiting spacecraft. "We have spent decades preparing for the possibility of receiving radio messages from distant stars," he notes. "We are far less prepared for the possibility that advanced civilizations might be studying us directly through reconnaissance missions." This lack of preparedness extends to governmental and institutional responses. While there are protocols for handling potential SETI detections, they are based on the assumption of contact through electromagnetic signals, not physical visits. The 3I Atlas phenomenon underscores the need for comprehensive frameworks that address all possible manifestations of extraterrestrial intelligence, including scenarios that might require immediate rather than contemplative responses. The implications for space exploration policy are just as significant. If interstellar visitors are indeed present in our solar system, future space missions might encounter artificial objects or evidence of extraterrestrial activity. Space agencies must take these possibilities into account when designing exploration programs and developing contingency plans for unexpected discoveries. NASA's Planetary Defense Coordination Office, which was established to track potentially hazardous asteroids, has started to include interstellar object monitoring in its mission scope. This expansion shows a growing acknowledgement that unusual visitors like 3I Atlas deserve careful tracking, regardless of their final origin. The office's dual focus on natural hazards and potentially artificial objects is an important evolution in space surveillance priorities. The confirmation that an object like 3I Atlas is of artificial origin would be the most significant discovery in human history, fundamentally changing our understanding of our place in the universe. Such a confirmation would prove that advanced civilizations exist, have interstellar travel capabilities, and see our solar system as worthy of investigation. The consequences would reach far beyond astronomy, affecting philosophy, religion, politics, and every part of human culture. However, the standard for such a confirmation must remain exceptionally high. The history of science is filled with examples of initially promising anomalies that were eventually given conventional explanations. The canals of Mars, pulsars, initially nicknamed little green men, and various supposed biosignatures have all shown the risk of jumping to conclusions about extraterrestrial phenomena. The 3I Atlas case might in the end be another instance of human pattern-seeking behavior, finding artificial meaning in natural randomness. The object's trajectory, though statistically improbable, might just be an extraordinary coincidence rather than proof of design. Only continued observation and analysis can resolve these questions for certain. Yet even if 3I Atlas is found to be entirely natural, its effect on SETI methodology and thinking will be lasting and profound. The object has shown that interstellar visitors can be detected with current technology, and that subtle signs of artificial origin can be identified through careful statistical analysis. These lessons will guide future searches regardless of 3I Atlas's ultimate nature. The case has also emphasized the importance of interdisciplinary collaboration in SETI research. Understanding objects like 3I Atlas requires knowledge in orbital mechanics, statistical analysis, material science, and many other fields besides traditional radio astronomy. This collaborative approach may be vital for recognizing and interpreting genuinely artificial phenomena when they finally appear. 3I Atlas is either humanity's most profound discovery or its most elaborate cosmic coincidence. This 7-mile-wide visitor from interstellar space shows all the signs that the dark forest theory would predict. A meticulously arranged trajectory with 1 in 2,000 odds, an untouched composition suggesting ancient origins, and a series of planetary flybys that looks like a reconnaissance mission plan. Yet for all its anomalies, the absent cometary gases, the statistically improbable path, the strategic timing of its hidden perihelion, 3I Atlas falls just short of giving the conclusive proof that would confirm we are not alone. As it finishes its grand tour of our solar system and heads back into the cosmic darkness, this enigmatic object leaves us with the most tantalizing question in human history. Are we witnessing first contact through the Black Forest's silent watchers, or simply the universe's most remarkable coincidence?